All right, our last note is going to be on polymerization reactions. We're going to look at two different types of polymers, polymers that are made with an addition reaction and polymers that are made with a condensation reaction. So our first sort of step is to look at synthetic addition polymers, and then we'll look at synthetic condensation polymers. So first off, polymers. What is your definition of a polymer? Polymer is a very long molecule that is made by linking together many smaller molecules called monomers. So kind of like you can sort of visualize joining paper clips together in a long chain where each paper clip represents a monomer. Polymers can be made of just one type of monomer or a combination of two or more different monomers. So here are some examples. So in the first example with all the A's, we've got just one type of monomer repeating over and over again. In the second, third, and fourth examples, we've got two different monomers. We call them A and B, and they're repeating in different patterns. So there's no one set of rules for how these monomers have to link together, and that's what makes organic chemistry really cool, is that there are a lot of possibilities to link these monomers together, so that, that makes polymers very, very diverse. So last little definition there, a polymerization reaction is how those monomers get joined together to form polymers. So some examples of natural polymers. Wood, which is actually monomers of glucose that are bonded together. So if you've taken biology, you know that sort of each one of these rings here is a glucose ring. So those are sort of your glucose molecules, and you can see that it's bonded together with a COC bond. Hopefully you remember a little bit that that's an ether bond, okay? So we link a bunch of glucose molecules together, that makes wood. Proteins are a polymer of amino acids. So if you, again, took the grade 12 biology course, you know that you've basically got an amide bond happening in each one of them. And the different amino acids are basically dictated by these different R groups attached to the carbons, okay? Now, if you haven't taken grade 12 biology, don't worry about it. The only thing I want you to realize here is that you have an amide bond happening with your carboxyl group or carbonyl group, sorry, bonded to a nitrogen. So you've got repeating, if you can see, amide bonds over and over again to form these big long chains of amino acids, and that's basically how proteins are made. Last example of natural polymers that we see are nucleic acids. So basically this is how DNA is made. And you can see lots of different monomers happening here. We've got the sugar phosphate backbone. So here's a sugar, and there's a phosphate, sugar, phosphate. So there's alternating monomers there within that chain. And then there's also your different branches off of that. So your different nucleotides that basically make up your DNA. Okay, so those are also attached and make up all your different molecules of DNA. So general classes of polymers, you can have chain growth, which is addition polymers, and this is often used, we need a free radical to be able to do this. Or we have a step growth, which is a condensation polymer. That's the second one we're going to do. So we're going to look at addition polymerization first. This is a reaction in which monomers with a double bond, so we have an addition reaction, you're already familiar with that. The double bond join together through multiple addition reactions to form a polymer. So what happens basically, remember that your basic addition reaction happened when you have a double bond. One of them broke and opened up so that those carbons could bond to two new things, okay? This is going to be the same process, but a little bit more complicated because we're going to have lots of double bonds linking lots of monomers together into a polymer. So there's actually three steps here. There's the initiation step, the propagation step, and the termination step. So step one is initiation. You first have to generate a radical initiator. So that means that you have to basically use a radical such as benzoyl peroxide, okay, to start the process going into start by opening up one of the double bonds. So basically you can see here that if we take benzoyl peroxide, you end up with this radical indicator. So we use the symbol IN with a dot. That dot symbolizes a free electron that is basically the free radical that will start the process happening, okay? So what happens here, we basically cleave this molecule in half when we add heat, and that's how we get two of these, and you can see it almost looks like a carboxylic acid, but I'm missing an H here, okay? So because I'm missing an H, that oxygen basically has a free electron that's ready to bond to an H or to bond to something else, but there's nothing there for it to bond to. So it's very, very unstable, and that's what basically starts the process. So if we take this molecule and add a monomer to it, it's going to basically start the process of breaking these double bonds, and we're going to end up with a carbon radical. Then in step 2, what happens is we start to lengthen the chain. So we start off with a carbon radical, we add another monomer to it, we break another double bond, and we keep the chain going and extending longer and longer and longer. So the electrons shift in the newly bonded molecule, leaving one unpaired electron at the other end of its original double bond. This unpaired electron forms another covalent bond with another atomer group. And then the last step is the termination step. So this is when two carbon radicals come together to make a single covalent bond with no more of those free electrons and the free radicals on the end. So this basically is how that whole process would stop. So I know that all these terms are very new for you, and you might be a little bit confused as to what happens. So I'm going to take you through it sort of step by step again, using an actual molecule. So we start off with an indicator, IN, and it's a free radical, so it's got that free electron on it that I just showed to you in green. Okay, what it's going to do is it's going to kind of almost attack. Here's a monomer, okay? It's basically an ethene molecule with a double bond, okay? And what it's going to do is when it attacks, it's going to attack this carbon here on the end. When it does that, it makes that bond to carbon. So now, if you look over on my product side, my indicator is bonded to the carbon, and that carbon already has two hydrogens on it. So that's three things that it's bonded to. It can't still make a double bond to the next carbon. So that's how the double bond basically gets broken and kicked out and basically thrown onto the last carbon. So again, just to recap, your indicator or your free radical comes in and bonds to the carbon, which bumps out one of the double bonds. When that happens, now this carbon is basically bonded, this carbon is now bonded to four things. The double bond is broken, but now the second carbon here, I'll do this in red, the second carbon here still only has two hydrogens, but it can't make this double bond anymore because the first carbon can't have 5 bonds. So what does it do? Well, it sits there with basically a free electron on the end waiting to make another bond with something else. That basically makes, it's called a radical intermediate. That's your carbon radical, because now my free electron or my radical is sitting on a carbon atom and not on an indicator. So that's sort of your first step to initiate the chain. Now we're going to take the same molecule that was in my product, and that's going to become my reactant for the next slide. Okay, so there it is, right there. Okay, with the free radical or the extra electron on the carbon. If I add another double bonded monomer to it, what's it going to do? Well, remember, this carbon wants to make 4 bonds, and it's missing one, right? It's got 2 H's on it, but it's missing one. So it's going to come in and basically attack this carbon right here and make another bond. So now you've got basically, you've got your indicator at the end, and you've got 1, 2, 3, 4 carbons now in the chain. 1, 2, 3, and 4. When it did that, when it attacked that third carbon, it again bumped out the double bond, and that double bond now sits as a free radical at the end of the chain. So I'm basically, I can keep this going. So this is the propagation phase where I can keep making this chain longer and longer. So in the next one, I can add carbons basically 5 and 6. So this free radical here is going to come and attack, how am I going to draw this? A little bit squishy. It's going to come in and attack carbon 5, bump out this double bond and make the free radical over on this on carbon number 6. That's exactly what you see in the last chain. 1, 2, 3, 4, 5, 6, and there's the free radical on the end of that carbon. Okay, so basically it's a matter of just opening up these double bonds, but the way we do it is using a free radical that attacks it. So that's how these chains can get basically as long as they want to get. And then at the end, sorry, what happens is you have, I don't think I have a slide of this, so I'll put it on just in case. Is you have I'm running out of space here. Sorry. So you would basically have another indicator molecule, CH2, CH2, and it's got a free radical on the end of it. So that free radical can bond to that one. And now, as soon as that happens, now the chain ends. So that's how we terminate it. So there are many types of addition polymers, okay? Basically, we can look at this sort of easy sort of ethene molecule. But if we add a substituent group on it, so where that is, so that's not actually considered a sulfur, we call it a substituent group, we can change the type of polymer that we make. So if the substituent is a hydrogen atom, our monomer is ethene, actually, or ethylene is sort of the common name, okay? When we make the polymer of that, it's called polyethylene or polyethene because it's many ethene monomers joined together. So here are some other common monomers. So here you can see there's your polyethene. So we just showed you that. Here's another one where you would basically have a methyl group sticking off of this carbon. So instead of drawing it there, you can draw it down. But the same thing would happen. Your free radical would come in, attack that C, and bump that out. But what you end up is basically a propylene polymer, so polypropylene. Okay. Polyvinyl chloride is another one, so you've got chlorine attached to one of the carbons. Polystyrene is when you have a benzene ring attached to one of your carbons. And orlon or acrylan, again another one, but you've got a carbon and a nitrogen attached there using a triple bond. And the last one, your plexiglass, is kind of cool because you've got actually quite a complicated substituent group. So if you change the substituent group here or whatever it is, you can change the properties of the polymer. I've got some more on the next slide too, just to kind of show you. And you're not expected to memorize all these, so don't worry about that. Here's polyvinyl acetate, polyvinyl alcohol. That's what actually we're going to use in one of your labs. And Teflon. So you've all heard of a Teflon coating on a pan, that non-stick Teflon coating. Got some fluorines on there to make that happen. All right, so some properties of plastics really quickly. Plastics are polymers of substituted ethene. Okay, so if we change our substituent group, we get different types of plastics. They're chemically unreactive because once we've made that polymer, we have those carbon-carbon single bonds on a big long chain. And we know that if you just have an alkane, it's very nonpolar, very unreactive, so the same thing happens with plastics. So they're used for containers for chemicals and foods, etc. Again, because they're unreactive and they're not going to react with anything that's being stored in them. The intermolecular forces, you have some van der Waals forces. Sometimes you have a little bit of electrostatic attraction, so you might have some polarity based on the substituted groups that are on there. But again, you've got a really, really long sort of nonpolar chain. Plastics are also flexible and moldable due to their weak intermolecular forces. And let's look at some more substituted groups. So Teflon, I already told you, was this two carbons double bonded to each other, but they also have two fluorines. The strong carbon-fluorine bonds account for the unreactivity of Teflon and its non-stick properties, even at high temperatures. So why is Teflon good? Because remember, your fluorine is very electronegative. Oops. So you have all these carbon-fluorine bonds happening. It ends up looking like a big long molecule of carbons that has a bunch of fluorines on them. And each one of those, fluorines are very, very polar, okay, making this polymer bond together and stay together very quickly. So that's why it's sort of unreactive even at high temperatures, and that's how it develops its non-stick properties. Plexiglass. One of the H on ethene is replaced by the COOCH3 group. Okay, and that's responsible for transparency and optical properties, which is kind of cool. And the presence of the carbonyl group makes plexiglass soluble in other organic solvents that contain carbonyl groups, such as acetone. So what do you end up with? You basically have, oh sorry, I'll draw this down here because it's not, we're talking about Teflon, we're doing plexiglass. So you have your ethene molecule, but one of the H's actually has a C double bond O and O CH3. So you've got an ester sort of in there as well, which is kind of cool. And then what'll happen is this will open up and keep bonding to more ethenes and so on and so forth. And this ends up being your substituent group. All right, cross-linking is the last thing I've got to talk to you about this for addition polymerization. This occurs when monomers have two double bonds. The dienes have basically two locations where addition can occur, and what happens is dienes can attach two separate chains at the same time. This makes branches or bridges. We call these bridges crosslinks, and what they can do is they can hold the chain together and make that polymer even stronger. The amount of diene that's added dictates the rigidity of the polymer. An example of a cross-linking agent is 1,4-diethylbenzene. Okay, we're not going to do homework, so I'm just going to pull up the other slides on your condensation polymerization. Okay, and then we'll be done. So, we're going to look at another polymer reaction, so another way to make polymers, but this time it's going to be a reaction in which the monomers are joined together by the formation of an ester bond or an amide bond. So because it's a condensation reaction, we're going to make some water in the process. Each monomer must therefore have two functional groups, one at each end. This is used to make fabrics and fibers, and we're going to do an example of that. We're going to make some nylon fibers. So we have basically two difunctional molecules, so basically a molecule with two functional groups at either end. What that does is it can bond together to make a single molecule, and you can just keep linking the chain together. So here are some examples of condensation polymers. Dacron, which is a polyester, is used to make fabric for clothing and surgery. And nylon, which is a polyamide, is used in tires and making ropes and other articles of clothing. So let's look first at polyester. Okay? Condensation polymers that contain ester bonds are called polyesters. Results from the esterification of a dicarboxylic acid and dialcohols, or monomers containing both a carboxyl and a hydroxyl group. So I'm going to show you some examples of this. The ester linkages are formed end-to-end between alternating acid molecules and alcohol molecules. And here's basically how it works. So here I have a molecule. So ignore my little box for now. This here is a molecule. This is called a dicarboxylic acid because I've got a carboxylic acid group on that end and a carboxylic acid group on the other end. Okay. What I'm going to do is link this with this. Actually, I'll color code this a little bit for you. And I'll do this in blue. Okay. This is a dialcohol. So you can see I've got two OH groups on here. So here's a dialcohol, and this is a dicarboxylic acid. So we know, in general, that an ester is formed when we link a carboxylic acid and an alcohol together. So what's going to happen here is, you can see the way that I've taken my box, I've basically removed H2O and made an ester linkage. So this carbon here is going to now bond to this oxygen over here. Okay, that'll bond together. That made this bond right here. Okay? So now what you end up with is a molecule that has a carboxylic acid on one end, and this is technically an alcohol on the other end. So if we get another molecule, say another dicarboxylic acid, and add it over here, we can make another ester bond. If we get another dialcohol and put it over with the carboxylic acid again, we can make another ester. So that's how these molecules get bigger and bigger. Polyamides work the same way, except we're going to make an amide bond instead of an ester. So you're looking at making a condensation reaction between a carboxylic acid and an amine. And again, your monomers must be dicarboxylic acids and diamines, or monomers that have one of each on each end. So a couple of examples. Nylon 66 is a polyamide. Kevlar that makes those bulletproof vests is a polyamide that has cross-linking in it. So just some cool examples. So again, let's take a look at what I've got here. Ignore my little boxes. So here I've got a diamine. So you can see I've got an amine group on one end and an amine group on another. And here I've got a dicarboxylic acid. Again, just like on the last slide. Ileic acid. Okay, and if I just take those two molecules and sort of don't worry about the rest of this for now, but if I just take those two molecules and I do my condensation reaction and I remove H2O, you can see I'm going to make an amide bond here at the end. So this nitrogen is now going to bond to this carbon over here. So that's what happened. The nitrogen down here bonds to that carbon, and there is your amide bond, or your amide functional group. Okay. The reason why this molecule can again keep getting longer and longer is because what do? Well, now we can keep adding. Here's the same diamine again. So the key thing here is that each one of these molecules has two functional groups, one at each end, so that both ends can react, do your condensation reaction, and keep the chain growing. So if I added on another dicarboxylic acid, I could again make my chain even longer. So again, here's another sort of picture of how this works. I've drawn this with sort of the condensed formula, so you can't really see all the bonds as well, but we can sort of still talk our way through it. We're going to take one of these hydrogens and a hydrogen and oxygen here to make your amide bond. Okay, so that's your amide bond right here. Okay, so this water comes off and is there. Okay, so you make your amide bond. Now if we look at this molecule here, we've got a carboxylic acid on one side and an amine on the other side. So I can add either a carboxylic acid on this side and make an amide, or I can add an amine on this side and make an amide. And in both cases, I'm just extending the chain longer and longer and longer. All right, so that's pretty much it for polymerization. We're going to go through some more examples in class, and we're actually going to make some of these synthetic polymers. So hopefully that will help in your understanding. And if you have any questions, we'll take them up in class.